share my
Yes,
screen as well.
we can start.
All right. All right. Okay. So, good evening, everyone. Just want to confirm if everybody can see me. If you can see
Yeah, we
me
can.
and you can hear me, um, just signify. All right. Great. Great. All right. Thank you. All right. So, I count it. My name is Ayomide. You get to know about me very shortly. But first, let me get to thank your president, Ahmad Sabri, and the executives as well, the of the Association of Civil Engineering Students for giving you guys the opportunity to have webinars, turn and gowns like this, where I get to be exposed to people in the industry as well. So I count it a privilege as well to be here with Kenyatta students, and I'm going to be giving a presentation on making it stand. So it's going to be quite an interesting program, and I do encourage everyone, as much as possible, to ask questions. I would like to make this session a lot interactive. Okay, so your president just before he started, he asked what your expectations are, and he's kind of done that ahead of time. um the reason I love that question is that before you come to a program, you should have something that you want to live with, right? You should have something that you feel that should stick with you, or else there won't be any point in the program, right? So let me quickly explain why I'm here, also so you understand yourselves why you're also here as well. My name is Ayomide Akinrinade, like I mentioned earlier. I am a practicing structural engineer in Nigeria, Africa, proudly African as all of us are. I am also the founder and CEO of DANSTRUCT 18, which is a young structural AEC firm. So we do focus a lot on designs in the industry in our firm, and we also produce AC solutions as well. So these are more or less solutions that help to aid in the area of architecture, engineering, and construction. So more advanced solutions in that area. We also provide trainings and services to other professionals in the industry. We also give out. We also have outsourced services where we get to partner with other consulting firms and construction firms as well in delivering projects to stakeholders and clients. Well, I'm really sure that's all just talk. You don't want to know about that. So what am I here for, right? Right in this meeting today, to make it stand out from your regular classrooms. And also I must also thank everybody as well for joining me. I believe this is should be 8:22 in Kenya, if I'm right. It should be 8:22. So I know that's quite late by our standards here. So I do appreciate everybody that has joined this meeting so far. All right, so thank you. So I'm here to talk to you about making it stand. And like I mentioned earlier, my name is Ayomide, and I am a structural engineer, and also I've talked about my company. And this particular program that I'm going to talk about is something that I've done over the past 2 years now, and it's more or less educating civil engineering students and other students in the AEC field. So that could be architects, builders, quantity surveyors, or any other people related with the AEC industry on the foundational principles, you understand, that go into building design. And I believe it's a very important topic because there are some very key things that we do learn in school, but unless we actually see how it's being practiced or actualized, we actually don't get the concept. So I am very happy to be doing this as well today. And like I said, I really want to make this very interactive. So if you do have any questions, let me know. You could also send your messages to the chat box, or bring the attention to your presidents or other executives as well, so we could go through them. All right. So making it stand is the topic. Well, what exactly are we making stand? So we're talking about buildings, right? More or less, just want to get a quick head count. Let's see how the vibe is in the room. Everybody here right now, the majority of the students in the association are civil engineering students. If that's the case, let me just see hands, the emoji option. Let me just see that. So a majority of you are civil engineering students. Just want to confirm. All right, great. Okay, yeah, so we have quite a lot, and everybody is in different levels. So buildings, it's not anything new to us. In fact, when we were picking the choice of course, right, for a lot of us, we actually had interest in buildings, right? Whether it be in construction or the design process as well. But the buildings don't just come just like that, right? They don't just appear just like that, right? Behind the beautiful architecture, that's the aesthetics, there's something that makes a building stand erect. There's something, or rather, the skeleton behind the building that makes, all those aesthetic, all those functions, happen. Right? And that's the beauty of structures, right? And I myself, a structural engineer, can relate to this as well. All future structural engineers as well in this meeting can relate to this as well. So let's talk about buildings now. Let me see. How many of you are familiar with this? Like I said, I'm going to make this very interactive. I've created a slide to do such. So how many of you have seen this before? This should be a little bit more common to, let's say, the fourth year students, third year students. I'm not sure of the second year students, but let me just see by hands. How many of you have seen this before? Okay. All right, I see a comment from Bethel. The audio. All right, I just want to confirm if anybody else is having issues hearing me. Just want to confirm. If you're having issues hearing me, let me know. Okay. Just want to confirm. All right. Okay. All right. I'll continue now. All right. But if there are any issues, okay, it's gotten clear. All right. Perfect. Great. So thanks for the feedback, Beto. So yeah, so a lot of you are familiar with this, right? And believe me when I say that this, right, you may actually understand it for the classworks and the exams, right? But exactly what its function is, a lot of us don't get it even after, our graduations. It's just kind of to do and to get done with it, right? And we're actually going to be breaking everything down and explaining exactly what this is. So all the way to this, for instance, now some of you are familiar with this, right? Let me just get by hands. Like I said, very, very interactive. Let me see by hands again. If you are familiar with this. Okay, great. I will explain what all of these are as we go on. All right, so you've seen something like this. Then this, right? So let me see if you guys know what this is. So, okay, by comment in the chat box, who can identify what just came on top of that diagram? Let me just see by comments in the chat box. Okay, UDL. Okay, Ahmad signified that that is a UDL, which stands for Uniformly Distributed Load. Let me see if anybody else. Okay, UDL as well. Okay, UDL, UDL. Okay, great. So how many of you actually know what a UDL is? If you don't know, feel free to say you don't know. I just want to, get this feedback. So if you don't know what a UDL is, just say I don't. If you know what it is, just say I do. All right. So UDL. Okay, great. All right, great. I love the honesty, right? So William said he doesn't know, and that's one of the important things about this meeting. We're breaking everything down, discretizing it, to very simple concepts. Now, all of these are textbook, right? When I mean textbook, um, it's easier said than done when we learn it, but applying it is a whole different game, and that's exactly what this program is about. Now, we're talking about buildings. Let's break it down, right? Buildings are a combination of various things, right? Buildings are a combination of elements. We call them structural elements. And you can see in this diagram over here is what a lot of us actually refer to as skeleton. I don't know if many of you have heard this term before. So it's also referred to as what we call the structural frame. And the structural frame is the combination of different structural elements. Okay, and we're going to be breaking all of those down. So let's talk about these structural elements. Like I said before, if you have any questions, just let me know. So what makes up a building structure? So this frame that we see inside here or in different buildings that we are in, what actually makes up the frame? So let's start with this. Um, a lot of us right now we're probably sitting down, standing if you are diligent. But we are probably sitting down in a building, right? A lot of us may be in a building. We may be, on top of a floor, for instance, right? And that's actually part of the building, if I must say, right? We not want to understand what the function of all of these elements are. So let's start off with something simple. So what makes up a building structure? The first one I want to talk about now is the columns. So how many of you know what columns are? Let me see by hand again. You know what a column is, or rather, you've heard of the term. Okay, great. So, columns in this case are vertical members through buildings, right? And We have basic classifications of columns. So for instance, we can't have just decorative columns like you've seen in some of these Roman Empire prehistoric structures, right? Those very decorative columns, they just design them, right? Those serve as aesthetic architectural columns. But columns play a very vital role in buildings because without the columns, we're probably not going to be sitting down as we are. That's quite dark, but we're probably not going to be, comfortable sitting down where we are right now, especially if you are, on an elevated level, right? So what columns do, for instance, is that they carry loads from other elements, and we'll talk about these other elements very shortly, and then transfer the loads all the way down. So for instance, now, let's not think about this too technically, right? If I always love to show examples, right? So I have this bead over here, right? So I'm holding up the bead in the air, right? And my hand over here, I can call this, for instance, a support, right? When I let go of the bead, right, that particular item has been subjected to the force of gravity, right? Every single thing that goes up must come down. Everybody knows that, right? We did that probably in our preschool, secondary school, right? My hand in that case served as what we call a support, right? And I allow that item to fall because there isn't any other supports on it, right? And basically what columns do is that they carry all the loads of some of those similar elements. So for instance, it could be those beams, right? And then they hold them in place. So in this case here, I'm holding this up so it doesn't fall, right? But once I'm no longer there, in this case, the column, that item is just subjected to the force of gravity, right? And as you can see in this image over here, for instance, the column is connected to various floors. So you can see them. Let me move my cursor. Let me see if I can do this. So you can see here that it connects various floors all together. So this floor, this floor, this floor, this floor. And the loads are being transferred to the column one by one, right? Okay, good. Now, you would notice that anything subjected to gravity, as it goes down and is collecting more loads, is going to become a little bit heavier. Let me use the word heavier, right? So that means the internal forces inside the columns, because we can't see those forces, right? They become a lot more as we go down, as it's, as we go down, it's carrying more loads. And what you would have noticed, for instance, if some of you that may have done your internship, for instance, and you've worked in construction, you will notice that as columns go from floor to floor, they become thicker, if I may say, right? So let me just get this. Has anybody ever noticed this before? Okay, so Stephen, right? So Stephen said he's noticed this before. For those of you that have had that construction experience or probably design experience, you've noticed that. Okay, great, right? So that's one of the reasons, right, for why columns, the cross sections of columns become thicker, right? Because the loads going to them become heavier. Okay, so that's one element of the building. The second element of the building I want to talk about now are beams. So we refer to this sometimes as girders, joists, depending on the function of that particular element, right? So what exactly do beams do? Beams are basically referred to as horizontal. Generally, they are referred to as horizontal structural members. Not necessarily always going to be horizontal, they could be inclined as well. But what actually gives them the name beams means that the loads are directly imposed to them on this plane, right? So for instance, now let's assume this is our beam, right? The loads are imposed to it in this particular direction. If, for instance, the beam was inclined like this, right? As long as the loads are still imposed to it in this direction, it still functions as a beam. If, for instance, now this, we look at this as a member, many of us may be quick to think this is a column. But the questions that we should be asking, for instance, is where exactly are the loads imposed to on this particular structure? If they are imposed in this direction, for instance, now it still functions as a beam. Now let me give a quick trivia. If, for instance, the loads are imposed on this particular element from this top, what does this make this element? So let me just see by hands. Let me see if you can get that in chat box. If, for instance, all right, so Ahmad Sabri said, okay, it functions as a column. Let me see if anybody else has any comments on that. All right. Okay, Felix said column, column, well, great. You guys are doing great, right? So also, depending on how that particular element or rather structure element is loaded, right? That's how you determine what it should be analyzed and designed as. And we'll get over to analysis and design shortly. Okay, so like I mentioned, right, beams are horizontal or inclined members as long as the loads are acting directly along the span, right? Now they can be used in foundations as well, grade beams, foundation beams. and they refer to those as elastic members, right? Now, beams are generally used as a means of reducing tension in elements because those beams, for instance, collect loads from the floor slabs, right? If, for instance, you are on a suspended floor slab, right? You probably can't see those beams that are below you. What you're saying is the slab, right? What is actually happening and you can't see, those are what we call those internal forces, is that the loads from the slabs, for instance, are going to the beams, right? And as they get to the beam, for instance, let me bring back my pen, love this illustration, right? The beam is subjected to bending, right? And for instance, now it's going to feel most of the bending at the bottom. And that particular bending there is what we call a tensile deformation, right? So most beams, for instance, are always going to be designed against tension, right? And if, for instance, it's the loads are quite much, they will be designed against tension and compression. I'm probably sure many of you have heard this before. So that means that it's not just going to be designed at the bottom, it's going to be designed at the top as well. That's in cases where the loading applied to the top of the beam is quite much. So that's it. And also beams also play a very important function. So in cases where we have very, very tall structures, right? For instance, engineers and designers could place beams at certain points to improve the rigidity of a structure. Now, rigidity basically also refers to stiffness, right? So many of you have, for instance, seen truss structures, right? Where you see those interchanging members going all the way from one point to the other, right? Those kind of form a sort of aesthetics, but they also have a structural function as well. So they help to easily distribute loads between the building and as well also improve the stiffness of that particular structure. Okay, right. So that's a bit about beams. Now let's talk about you see. Okay, great. So just like I mentioned, if you saw this illustration, you see that the higher the loading on the beam, for instance, would require the beam to increase its depth. Okay. All right. So for instance, now if you are a designer and you realize that that particular beam doesn't pass right at a very small depth, what we could do, for instance, is we could increase the beam depth. And many of you would have seen this, for instance. So probably in your classrooms, you would have noticed probably a beam flying through the middle of the classroom. Those beams are quite thick, for instance. The reason for that is that those beams are carrying large floor slabs, and the larger the floor slabs, right, the greater the loads are going to be sent to those beams, for instance. Okay. Now we talked about slabs quite a lot. Now let's go ahead and now talk about it in depth. Floor slabs, right? So floor slabs, for instance, now are those panels or structural elements that we are basically always going to be interacting with on a day-to-day basis, right? So buildings, for instance, now are made up of floor slabs. Now, those are the actual main part of the building where we actually start to load it as human beings or whatever is meant to be the building is meant to be used for. And let me show you a pictorial view. For instance, you can see here that this structure over here, and I've indicated by arrows where the floor slabs are. So depending on the floor, they go from one floor to the other. All right. Now, you see that they collect the majority of variable loads on the structure. So for instance, now I am sitting right here now on a floor slab. If I move to the other side of the room, for instance, now I've basically moved from that area and that particular region of that slab is no longer loaded, right? And that's what we call variable loads, right? They aren't permanent like what we are, like our partition walls, for instance. So those are the block walls you see in your room, right? So that's what I mean by they carry a lot of variable loads, okay? Now, just like beams as well, they also designed to resist tensile loadings. So they feel most of their loadings, or rather their loadings at the bottom, for instance, right? But what distinguishes them from beams is that they have a larger area, right? And more or less, they are designed in two directions, unlike the beam where it's just designed in one direction. All right. Also, I also mentioned as well, if you notice in this particular diagram over here, you can see here that we have a slab, but you can't picture beams. So who can tell me what type of structural system this is? Okay, I'll talk about this very shortly, but let me see by indication in the chat box, who knows what kind of structural system this is, where we have the loads from the slabs going directly to the columns. Okay, let me see if anybody has a comment on that in the chat box. All right. Okay. All right, good. So let me mention that, right? So It's very possible, for instance, for you to have okay, Ahmad has no idea. Okay, great. So we're all learning every day, right? So the kind of system where we have let me probably move this to this next picture so we can see where we have, for instance, the slabs, the loads of the slabs going directly to the beams is what we call a flat slab system, right? I don't know if any of you have heard of solid slab systems, waffle slab system, ribbed slab systems, flat slab systems, right? So those are what we call structural configurations, right? So the cases where we use flat slabs is probably where we want to have larger spans or we don't want to have those suspended beams showing in the rooms, right? So buildings can actually be designed as well to have which can to be rather could be designed to have the loads of the slab go directly to the columns. But one of the things that you notice ahead of time is that those columns are always going to have a larger cross-section area, right? And also you notice that some cases where the slab spans are quite large, you notice the thickness of the slabs increase. All right, so I saw a beautiful question. I think I missed that, but let me go back to it. All right, so Amatabi said, could you explain the difference between the various types of slabs? Okay, great. Right, so that's basically what I'm doing right now. So flat slabs, for instance, now, the loads from the slab go directly to the columns and they have larger spans. One thing that you also notice about them is that they also have a significantly larger thickness or depth, right, or structural depth. For the solid slab systems, those type of slabs, for instance, are carried by beams. So the loading from the slabs are connected to the beams, right? And then from the beams, those loads from the beams go directly to the columns. And that's one that we're actually quite familiar with. Probably you see that in your dorm room, for instance, and you would have systems like that, or in smaller buildings like residential buildings, okay? We also have other floor systems as well, such as the waffle and rib slabs, where we have interconnecting beams within a slab panel. So you have larger beams, for instance, which could be, for instance, girders, and then we have smaller beams in within the system, which could be joists, for instance, right? So those kind of systems, they kind of form a sort of decorative function. And as well for waffle and rib slabs, they also kind of help to reduce the weight on the structure. Okay, so I didn't put that in this particular slide, but I would probably kind of share more on that probably to your community later on. Okay, so that's basically what we call the structural configuration. So back into floor slabs now. We were talking about okay, sorry about that. All right, great. So, like I mentioned also in my slide, they could also be supported either by beams or columns, depending on the structural system or configuration, as I may say. Right, so it could be flat, it could be solid, it could be ribbed, it could be waffle. And there are also quite a lot of other slab systems as well if you read and research on them. Right. Now, the next one I'm going to be talking about now is okay, right. So I put in an illustration, for instance, now where the loading on the slab, for instance, increases, right? And as a designer, you notice that particular slab is failing. What we as structural engineers tend to do is that we tend to increase the thickness of the slab, right? To make it perform or function as exactly what it was loaded to do. Okay. Now, going on here, we now talk about walls. All right, so let me stop here because these particular elements here are not quite common. But how many of us are familiar with structural walls? Not your normal, architectural walls, as you may see, but how many of you have come in across structural walls before? Okay, all right. So Duncan, okay, great. So Felix, all right, great, great, all right. So you guys are familiar with structural walls. So what distinguishes a structural wall, right? Okay, all right, great. So what distinguishes a structural wall, for instance, from a normal architectural wall? Okay, so structural walls are also panels just like slabs, but in this case, they actually rather do the same role as columns, right? So let me see. I've got quite a lot of items on my table. Let me see if I can get let me see if I can get a cleaner element I can use. All right, so I have my Bible over here, right? So let's assume this is a wall, right? Okay, great. So these walls, for instance, are tend to be structured. So that means they actually carry loads. For you to determine a particular element is a structural element, that means that it is carrying loads from the structure. In the case of walls, for instance, the loads are going directly to the top of the elements, just like beams. But what distinguishes it from beams is that beams, for instance, in this case, are just suspended elements. For walls, they go down just like columns. So those internal forces flow through the wall, and then they go straight down to the foundations, just like columns as well. So that is what how you distinguish structural walls. Now, for instance, if the structural wall was a concrete element, for instance, you will notice that those particular walls are always going to be reinforced, right? They will have what we call steel embedded inside them, just like you have your other concrete elements as well. I'll talk about those. Those are kind of materials. And also, you notice that for taller structures, we use structural walls to resist seismic, for instance, seismic wind lateral loadings on buildings, right? So they actually have those functions as well to reduce lateral drift. For instance, if you notice in countries that have high risk of seismic attacks, for instance, you notice that for taller structures, they tend to build them with core walls or shear walls at the edges, right? So those help to reduce what we call lateral drifting. So the building just, collapsing as it's shaking. Okay, so those are one of the functions as well. Also, they also have what we call functional benefits. So this kind of help, for instance, in the architectural aspect. So apart from being structural elements which actually are used to transfer loads, from floor to floor, they could also serve purposes such as shafts, for instance, your elevator shafts, for instance. So you notice that if you see in buildings, you notice that there are walls around the elevators. They could also be used as service ducts as well, depending on what the designers are looking to use. So I think I saw a question in the chat box. I want to make sure I address everything as we go on. All right. Okay. Okay. Great. Okay. So are they Steven said, are they the same as sway? All right. So great. Yeah. So it's very similar to sway actions, just like they are in columns as well. But in the case of walls, for instance, the once you introduce walls to a structure, right? For instance, let me give a pictorial example again. If you place a wall, for instance, in a building, right, and let's say, for instance, the wind loadings are coming from here, naturally this wall here is not going to sway, unlike when we have a slender element, for instance, like a column. So you see, like if you press a column like this, for instance, you can see that it sways, right? It's going to experience some kind of deformation out of its original position. But once you introduce, for instance, a wall, for instance, that's not going to be possible anymore unless the thickness, or rather, of the wall is quite small. Okay. All right. So yeah. All right. Great. Happy to explain that. All right, good. All right, great. Foundations, right? So every single element that I talked about earlier on are what we call superstructural elements, right? Apart from the ground beams that I kind of made emphasis on earlier. So superstructural elements include columns. They could include your suspended beams. They could include your suspended floors as well, right? All of those loads are now transferred to the ground, right? So like I mentioned earlier, every single thing is subjected to the force of gravity. Everything must go down, okay? Now, foundations help to transfer those loadings coming from the superstructure all the way to the ground, right? And depending on for instance, some factors such as loadings, environmental factors, and as well as the nature of the existing ground, it will determine the type of foundation that you use. So let me do a quick stop and ask, so how many of you are familiar with foundations? So you can mention an example of a foundation type that you've probably seen before or you've learned about. So let me get that in the chat box. Okay. So if you are familiar with a foundation type, let me hear that. Let me see your responses in the chat box. Okay. All right, good. So I'll wait for that. So like I mentioned, right, foundations are elements that actually take all the loadings from the superstructure, and they are basically referred to as what we call substructural elements, right? So we have various types of foundation. So I haven't gotten any comments about foundation types. So probably because of time, let me move on. So we have different types of foundations. Okay, great. Okay, I think maybe that was a lag on my end. All right, great. Okay, so we have shallow foundations, right? Great. So that's the classification of foundations. Under shallow foundations, we could have, for instance, pad footings. We could have raft footings. Okay, so Victor said raft footings. Great. All right. So if it's not a shallow foundation, it's most likely be the other classification, which is a deep foundation, right? We could have piles, board or drilled piles, right, which go straight down into the soil strata, into deeper depth, right? So for instance, now, if you probably heard this story, or probably in religious books as well, where we had the person that built, on top of poor grounds, for instance. So the building came down, So the foundation elements of the building, the structural elements of the building is very important because everything that you've designed, right, all falls down to the foundation, right? If you don't design a suitable foundation, the building is not going to stand. All right, so it will experience all sorts of effects such as the displacement, right? It could also experience also failure, sudden failure. Probably you've seen some of these disasters as well, and most of them are contributed towards poor choice in foundation or poor design or construction in foundation, right? So depending on some of these three factors like I've mentioned earlier on, the nature of the existing ground. If, for instance, you have a compressible soil, right, at the top, let's say the first 10 meters of soil is very compressible. What you may want to do, for instance, is that you may want to excavate that topsoil, so from 1 to 10 meters, and replace it with a more suitable soil type, and you're going to consolidate it. So consolidating means improving, you understand, the bearing capacity of the soil. But some of you are probably reasoning, for instance, now removing 10 meters of soil, especially for larger structures, might be quite expensive. So we're now going to be thinking as engineers, what other foundation type can I use? Okay, so I'll probably consider, for instance, a pile foundation, where I can drill or bore my pile into deeper depths. So for instance, 30 meters pile can go straight down until we reach a layer of soil that is suitable to carry the build. So some of these factors are what we look at when we're choosing foundations. All right. So after foundations, I also mentioned as well, foundations are basically supports at the ground or rather the soil level, right? And they can vary. So for instance, some could be lime areas, so such as foundation beams. Some could be areas such as mat foundations or raft foundations, as many of us may know is that. And then in the case of point footings, those could be your normal pad footings. Okay. All right. So that's basically how to also distinguish that. All right, so moving on, we also have what we call structural frames. So do not confuse it with structural configuration. Configuration means how the building, for instance, decomposes loads. So configurations such as solid slabs, where the slab loads go from the slab to the beams to the columns, or flat slabs in the case where it goes from the slabs directly to the columns. When we talk about building frames, we are talking about how the elements connect to each other. All right. So for instance, now we have two common types of building frames, and we have quite a number as well, but the two most common ones here are the rigid frames, for instance, where you can see a pictorial example on the left side of the slide, where we have the slabs connected to the beams, connected to the columns, right? So that's how that particular frame looks like. But for instance now, when we now have start to have what we call bracing, we now determine that that particular building frame has now turned into what we call a brace frame structure, meaning that that particular system is going to be a lot more stiffer. And I mentioned stiffness earlier on. So for instance, introducing, for instance, beams at particular floors will make the elements or rather the building a lot more stiffer in some areas. Now, we don't necessarily always have to do that on the horizontal plane. You can also do that in the vertical or inclined plane as well, right? And that's one of the beauty about structural engineering, because by modeling and trying out some of these options, we can see what makes a building stand better depending on the type of loading that we are applying to it. Okay, great. So that's just a quick demonstration on building frames. All right, good. So before I continue, if you do have any questions, do let me know as well. And just as we continue, I'm going to be talking about materials, right? Okay, good. All right, so Kenyatta students, right? I want to ask, for instance, what is the most common building material in your country or in your particular area? Okay, so let me get, all right, okay, I see a hand. Let me see. I see a hand from Ahmad. Okay, oh, yeah,
Yeah, that will be reinforced concrete. We haven't done much on structural timber.
okay.
I heard it's happening in Uganda, but it's something that is yet to happen in Kenya.
Mm,
Structural timber, that's sustainable structural timber, but mainly
okay,
it's reinforced concrete
okay, all right.
and steel.
All right, so reinforced concrete and structural steel. Okay, great. So let me see. Do I have any other hand as well? What is the common building material in your country? Everybody, a lot of us are from Kenya as well. So let's see. All right, so just like okay, so I see okay from Muyazi, right? So they said concrete as well. Okay, great. So materials used in construction, or rather, what are considered for design? Uh, Someone didn't just wake up one morning and say, let's start building with concrete, right? There are actually some factors that go into the choice of building materials. So for instance, if you look into the western part of the world, so that's America, you will notice that there's a very common building material which is used for mostly residential buildings. Who can guess what that material is? Or probably you know what it is. Who can guess what that material is? In the western part of the world, let me see, in America, let me see if anybody knows. For smaller residential buildings, what material do you think they use over there? Let me see if I can get a response on that. Okay, Ahmad, okay, has your hand. Okay.
Definitely like to give others an opportunity, but since
Yeah.
me raising my hand, they use structural timber mainly because of the temperature. It's very cold there, so you need an insulating material.
Hmm. All right. So temperature, right? So environmental conditions, right? And
Yes.
also availability of the material as well, right? So you notice over there, for instance, they use timber. Timber is a good material in insulating building structures, and you can also easily fabricate it as well, right? It's also a very sustainable material also, and that's one of the choice reasons why they tend to use that material more than concrete, right? But for instance, now you notice as buildings become a little bit heavier, right? They change the material choice to either, for instance, concrete or steel, right? So some of these are factors that are used in determining materials. So over in my own country, for instance, for residential structures, timber is not naturally the first choice. And it's like something that what some of us really need to ask as a question. So why isn't that material used as a first choice? So Nigeria, for instance, is in the tropical rainforest region of the world, right? So we are exposed to a lot of the weather conditions such as rain, right? And for instance, you would have noticed timber being wood, right, doesn't fare well under atmospheric conditions such as rain, right? It tends to lose its mechanical properties, right? And that's one of the main reasons why it's not used. Okay, so depending on the country, the region, the environmental conditions, available building codes, for instance, like I'll talk about earlier on, will determine the type of material that you use, right? So timber is a very, very good material. It is lightweight. And like I mentioned before, it's very easy to fabricate and it also allows you to form various shapes, right? So in contrast, for instance, concrete as well, is also a very, very resilient material, very strong material, and it has a higher strength compared to timber, for instance, and it could also be reinforced. So when I mean reinforced, that means that it becomes a composite material. So we embed, for instance, steel, and this is what we call reinforcing steel, not to be mistaken for structural steel, which will come up later. We can embed, reinforcement into the material, and we can improve its strength. Okay, so we also have concrete as a popular material, and concrete is very, very good in resisting compression loads. So, for instance, for columns, like I mentioned, concrete would be a very good choice for structural columns. But concrete suffers in tension. So, like I mentioned earlier on, beams which have most of the stresses developed at the bottom, for instance, yeah, concrete may not always be the first choice, right? We may want to consider another material such as structural steel. Okay, so steel compared to concrete and timber has very good properties in resisting tension. Now, if we come back to concrete, what we can do, for instance, is that to improve its tensile properties, we can now embed what we call reinforcing steel, just like I mentioned earlier on. And that's why you have elements reinforced in concrete, for instance, we call that RC concrete. So that's reinforced cement concrete, okay? So these are some of the reasons why we would consider some particular materials, so for construction, okay? Availability is also something that we should also look at as well. The cost also and the function. Okay, so these are things that we'll actually use in determining the material. All right, good. So now I've gone ahead and talked about some of the basics, of structural design. Now, if we have some of those foundational concepts, right, we know what type of material to use, we know structural configuration, we know what the building elements are, such as the columns, the beams, right, the slabs, right, trusses, and all of that, right. How do we use all those information to design a building, right? So I am the structural engineer and I have to determine where a structural element can be in a building. But I can't determine all these things without having what we call a referencing document, right? So our first point of contact is to reach out to an architect, right? And these are the professionals that are responsible for designing buildings in general, right? So what we do is that we get consulted by an architect, or probably if you are working in a big firm, you collaborate with your architects, and look at your design. Oh, this is really good, right? Always compliment the architects, by the way. That's good advice. And you look at the structure, right? Now, whatever is in the architectural drawing is not enough for the building to stand, right? We come in and say, okay, this is what we can do. This is where we can place structural elements. But this requires us to sit down and look through those documents. So for instance, if we're looking through 2D plans, printed drawings, we're looking through PDFs, or we're looking through BIM models, we want to look at areas that will be most exposed to loadings, for instance, areas that may prove problematic, areas that will call for concern, probably for rework or redesign. So we want to make sure that we spend a lot of time, looking through all these elements and making sure that okay, this can actually work, right? And you would have probably heard before. I don't know how many of you have heard this before. So, for instance, they'll say that you've heard this in the industry. Probably some of you have. The architect's dream is a structural engineer's, or rather engineer's nightmare. I don't know if anybody has heard that saying before. All right, great. Great. So it's part of the things in the pen, right? I don't actually see it as a nightmare. I see it as a challenge. So for instance, right? So the architect, for instance, is not particularly um meant to focus on the calculations or the physics, or of how a building stands, right? You understand what he's focusing on is the aesthetics and what the client is looking for. Now it is our job to be challenged by the architect, his ideas, and then bring all of that together and say, okay, can we make this work? If it can't work, are there any other suggestions, right? So all of this, we take our time and look through the model, right? So for instance, the arrangement of walls, the arrangement of floors, right? The arrangement, the levels, for instance, the height to height of floors. We look at all of this. I'm actually spending a lot of time there because as engineers or structural engineers, or probably project engineers as well, you really want to take a lot of time reviewing the architectural drawing before making decisions as you go over and prepare for your structural design. Now, with that being said, for instance, now we now go ahead and do what we call the arrangements of structural elements, right? Now, as you can see in this visual demonstration, right, we can see here that all of these elements have been hidden, right? They've been hidden inside the building to make sure that they don't defeat the function of the structure. Now, who can give me an example, or rather a reason why we have to hide these elements in the building? Let me see. Probably by hands, or you could also mention in the chat box. So why do we hide our structural elements in the building? Right, let me just see if anybody get that. All right, so okay, great. All right, so I see a comment from Jim. All right, so Jim is saying aesthetic, so probably referring not to defeat the aesthetic function of the building. All right, so the beauty, right? Yeah, great beauty. It won't be nice, for instance, you are sitting in the living room and you're watching TV, right? And there's a column standing in front of you. Unless you are a hardcore structural engineer, you don't really want to see that, right? So what, like I mentioned earlier, right? The structural frame is the skeleton of the building, right? You don't walk on the road and you expect people to see your skeleton. That's quite wrong and very disturbing, if I must say, right? We want to make sure that whatever is making the building stand is protected by the building core, right? So we now arrange these elements, and then we arrange it in a way that based on experience. And I mentioned this experience, very important, is that based on experience, you arrange them in a way that you feel it will be able to work, right? Now, this is kind of like an advice, especially for young designers. You don't necessarily always have to master the placement of elements, right? What you do is that you place them in a way that you feel it will work, and then you go over to analysis, which I'll talk about very shortly. And then, okay, determine, okay, probably I can move this element here, I can move this beam here, I can move this column here, and then we can now see how it works, okay? All right, so now we've arranged the structural elements, right? We now go over here to analysis. Before I continue, let me ask, right? So how many of you enjoy structural analysis in school, right? You probably I believe you should probably start structural analysis in your third year. All right. Okay, so if you do, all right. So it's probably the same thing as well. All right. So Aman has a hand. Okay. All right.
Yeah, just a comment. We're going to start structural analysis on our fourth year. So as with me, I'm going to start it in May, and if we have fourth years here, they've already done it. I'm going to do it in May. But this is very interesting so far.
Okay, all right, great. All right, so structural analysis, right? Yeah, it's very important, right? And the reason why I mentioned this is that we tend to, for most schools, I'm not sure if it's the same in Kenya, we tend to learn how to do structural analysis before design, which is actually the proper order of things, right? But what we do is that we probably, like for instance, you saw in the earlier presentation where you have those line diagrams. We are just seeing all of that and we don't know exactly what it means. Okay, I think I have a hand from Ahmad.
Apologies. I think I meant to say we're going to do design in fourth year. And yeah, structural analysis, we've been doing it since second year.
Okay, all right, in second year. Okay, great. Yeah, great. Because I know it should be the first, order of things, right? So we see all these line diagrams, these confusing frames and all of that. And what exactly do they mean? Those are what we call representation of those structural elements. So like you mentioned, like you saw earlier, for instance, now you saw, for instance, a line, right? And it was connected to two triangles, right? If I remember, right? So these are what we call representation of your structural elements, right? And what we do is that we now add loadings, like you saw those arrow diagrams earlier on in the presentation, right? What we do is that we load them and then we now analyze them to see how they react, right, under those types of loads, right? And structural element is the core is a very core part of structural engineering because it is where we get to determine, okay, for instance, how a particular element should be designed, right? Or what are the things that we need to look out for when we're designing the element? Is it going to be bending? Is it going to be torsion? Is it going to be shear? Right? And all of those things are very, very vital, right? And it's something that you would not necessarily always enjoy when you start, right? But once you see the practical aspects of it, it becomes the full beauty. And let me skip this here. And this is probably what I can show you, for instance, right? You load the structure, right? You do your analysis if you're going to be using software or you do it through manual design, right? You can now go and look at your elements and see what are those forces that are subjected to the elements based on how I loaded the structure, right? We can look at the bending, we can look at the axial forces, and these are things that you can't see with your eyes, but these diagrams show you exactly what is happening in that element. And all of these values are what you now consider when you go ahead and start doing your design, right? So a good encouragement, trust me, structural analysis is very beautiful once you get the hang of it and you can apply it, right? Now, when you've analyzed your structure, right, it doesn't stop there, right? You're just beginning. You go ahead and now prep for your design, right? So you are taking in those values, you are considering those values as well as some other preliminary values. For instance, right, you do make a lot of assumptions, as a structural engineer, and this can be based on your experience. This can be based on what you've been exposed to or based on the preliminary data that has been given to you, for instance, right? So if you have a beam, for instance, you have some information about its cross section area, right? You know what has been loaded, you know its values. Now, aside from all those geometric information and preliminary data, we now have to choose a code, for instance. How many of you are familiar with design codes, right? So please don't pay attention to this slide for now. It's going to be on repeat, so I could show you that. So how many of you are familiar with design codes, right? That's structural design, building design codes. Let me see hands. All right, so Felix has a hand. Okay, great. Okay, Duncan has a hand. Okay, great, right. So if let me just give it or simplify it like this. Okay, better said, okay, no, okay, great, right? We can't leave human beings to determine how structures should be designed, right? Especially for instance, contractors. People will get away with a lot of things. If, for instance, you get to a construction site, you're probably a project engineer. And what is on the drawing, for instance, is there should be three numbers of 16 members placed at the bottom of the beam. If another engineer should walk in to the area and say, no, place two numbers of 16 members at the bottom of the beam, right? There's going to be quite a lot of confusion. Now, what exactly determines what the number of bars should be, for instance, in a reinforced concrete element, is what we call a building design code, right? So they have laid out instructions. It's probably like I refer to it, for instance, like a rule book, right? A constitution for structural engineers to follow to determine how a particular element should be designed, right? So not everybody will just have their own idea, for instance, on how an element should work. So all of these have been written, or rather been researched, and then they've been published for us structural engineers to use for the design of our elements, right? So we use all of those information, for instance, to perform the design of some structural elements such as our beams, as you can see in this demonstration. And there's quite a lot of inputs that goes into it. So for instance, you are going to specify the cover, you're going to specify the material, what type of concrete material are you going to use, if you are using concrete, if you are using steel, what section shape are you going to be using, if you are using timber, what section are you going to be using, what is the grade of steel, what is the grade of timber, right? So all of this information, you put it and consider it in your design, and then you come over and you get your functional design. Now, it's not every case where you're going to have a design that passes, right? Now, we now go back to our foundational knowledge, for instance. If, for instance, I have a beam of a particular depth, right? Let's say it has a depth of, let's say, 300 mm, and it's failing, right? And let's say, for instance, it's failing in tension, right? What can I do in that case to make that beam pass? Just by using our general physics, term, right? If we have a beam, for instance, which has a depth, so the depth is the thickness of the beam in this direction of 300 mm, right? And it is failing based off of my design. What can I do to make that beam pass, right? So you can just guess if you don't know. Let me just see just by hands, right? You just guess. All right. So there's quite a lot of things that you can do to make a member, pass in the design, right? And that's based on some of the things that we talked about earlier. So I mentioned, for instance, a beam, for instance, is poor intention. So okay, I see a hand from, okay, I might say increase the depth. Great. So increasing the depth, so everybody is on the same pace, right? So by increasing the depth, right, we're increasing the strength of the concrete at the bottom, right? So we can do some of these things to structural elements. So just like I mentioned, for instance, on columns, if the loading becomes so much on the columns and the particular section, for instance, is not passing, what we can do is that we can increase the section of the column. If, for instance, the column section was 200 by 200 and it's failing, what we can do is that we can increase the column section to, for instance, 300 by 300, and we check again and see if it passes. So the design stage is actually an iterative process. So meaning that if it fails, we go back and redesign, changing some information, and then we come and check if it passes, right? So that's the design stage. Okay, great. Now we have designed, and probably this is where we think we can go and sit down and rest, right? But a design is not complete unless it can be documented and represented, you understand, to whoever, whichever professional is going to be using it, for construction, right? And this is actually a very good skill, a very good skill for us young engineers as well, especially before we come out of school, because it demonstrates our knowledge of how elements, for instance, should actually be arranged or fabricated for construction, right? So we produce what we call detailed drawings. I don't know if you guys are familiar with the term detailed drawings. So construction drawings, those are the drawings that you see on site that determine, for instance, where this member should be placed. Okay, Philip said yes. Duncan said yes. I want to see if I have a no. Right, let me see if I have a no. Okay. All right. So great. If you haven't seen, okay, great. Right. So structural drawing. So some of you have probably seen this in your assignments as well. So every single thing we've done, all the okay. All right. So Paul said no. All right. Great. So every single thing that we've done so far, from the analysis, design, determining the material, right? Everything falls down to the structural drawings. This is what we send, right, to people that may not necessarily, for instance, be engineers. Yes, and to actually go ahead and produce those things in real life, right? So it's more or less like our communication medium. You can't just walk to a construction site and say, okay, put this beam of this particular length here, I provide this reinforcement or provide this steel section here, right? It's going to be like, what is your documentation? What is your proof that, okay, that this will work, right? Everything needs to be documented rather, in a proper way, so we understand how these elements work together. Okay, all right, great. So documentations will be your structural drawings, and they are normally also coordinated with what we call the architectural drawings, right? So you would have seen, for instance, in some cases where we have the structural drawings not aligning with the architectural drawings. So that's why it's important that you always coordinate your drawings together. Coordination just means that you are making sure that whatever is in the structural aligns with the architectural, meaning that I don't have that ugly column standing in front of me as I'm watching TV, right? We don't really love structures that much to have that kind of, disparity. in our building, right? So yeah, so that's it, right? And that's basically the whole process of structural design, which is basically the concept of this making it stand program that we held today, right? Now, I would love to, answer and address, your questions. I really want to get questions, if you do have, and you could also start sending them in. But before we end the program and I hand it over to your president, you understand, for no more remarks, I would like for us to do a very short exercise, right? I would encourage everybody as well to participate. Like I said, I really love interactive engagement, and I would like to see how you think, as engineers, young engineers ourselves, on particular problems that we may face when we are doing structural designs, right? All right, now look at this particular image on the screen, right? So we see, let's assume those two lines, those two black lines in the vertical directions are columns, and the horizontal member is a beam, right? Let's say red indicates that that beam is failing, right? What can we do to make that beam pass? Okay, so now out of each questions, we have three options. So the first option is this, right? So this is option A, right? So if you feel option A is the best option, just type option A in the chat box so I'll see your recommendation. Now, there is no wrong or right answers. It's just based on our experience or how we understand structures. That's how you answer it. All right, so this is option B. All right. If you didn't notice or I didn't see it, just let me know so I'll go back to it. And this is option C. All right, good. So let me take it again. All right. So if we have a structure like this, right, and the beam is failing like this, what can we do to make it pass? Option A. Option A in this case is introducing a column in between the beam span. Option B is increasing the depth. Option C is extending the columns into the beams. All right, let me see your comments. All right, great. All right, great. So I love how everybody's response differs, right? And this is based on your experience, right? It's based on how you reason or a particular structure is actually meant to behave. All right, great. So let me see your options coming in. All right. So because of time, if you are responding, just say this respond for the beam problem. So write beam, then put in the option that you choose. All right, so let's look at another problem, for instance, right? So let's assume the four red lines shown in this diagram here refer to columns, okay? So we're looking at a column challenge now, right? And the four black lines at the top here are beams. These particular columns here are failing, so they're indicated as red. So just like the beams, we have three options. What can we do to make them pass? This is option A, right? Option A is looking like we increase the thickness of the column, so increasing the cross section. Option B, we're bracing it, so this is a brace system. And option C, we're introducing beams at an intermediate point of the columns. Okay, so let me take that again. All right. Okay, great. So I love the responses on this, right? All right, good. All right. So if we have four columns like this, slender columns, I must say, and they are failing, right? What can we do to increase or rather to make these columns fast? Right. So option A would be to increase the cross section area. Option B will be to brace the columns. Option C will be to introduce, beams at an intermediate spot in the columns. So let me look at the responses, right? Okay, great. All right. So I'm seeing B's. I'm seeing some A's. I'm seeing some C's as well, right? Right. So I might say that B is more affordable, especially in high-rise building. Altering the columns will make it expensive. Great. That's a good response. All right. Okay. Okay, Steven said B. B, C would have been nice, but it would be costly. Great. So you guys are considering all these factors all together. And that is what we do as structural engineers. We consider some of these factors when we are determining rather fixing a problem. Now let's look at one more challenge and then we'll call it meeting end, right? So in this case here, we have a slab problem, right? So this particular slab, for instance, here is failing, okay? So what can we do to make this slab pass? So the first option, for instance, now is that I introduced a beam in between the slab span, okay? That's option A. Option B is that I introduce smaller beams in between the slab spans. And option C in this case here would be to increase the depth of the beam, of the slab rather, sorry. Okay, so let me take it again from the beginning. All right, so we have a slab here which is failing. So the first option will be to introduce a beam, right, in between the slab. Option B would be to introduce smaller beam segments in between the slab area. And option C would be to increase the depth of the beam. All right, good. So let me see their responses on that. All right, so I'm seeing C's, I'm seeing A's. So the beauty of this is that everybody has different answers, and that's based on how they look at the problem, right? Like I mentioned earlier on, there is no right or wrong answers, because what we need to do as structural engineers is that we need to ask questions, for instance, right? We need to get information. For instance, what is the span of the slab? You understand what is the material for the concrete, or rather the elements that we're considering for the design, right? And all of this is culminates to what we call, our design experience, and we cannot determine, okay, what particular solution works best, right? So, right, great. Thank you guys so much. I really enjoyed the engagement on that. All right, so good. So that will be the coming to the end of my presentation for today. I do hope everybody had a great session. I did myself, right? And like I mentioned, my name is Ayomide Akinrinade, and I am a practicing structural engineer in Nigeria, right? I am also CEO and co-founder, and also structural engineer at DANSTRUCT 18. So I've left some of my details over here, and feel free to reach out to me anytime. I'm an open book, right? You can send me a message on LinkedIn, send us a mail, and we would reach out to you. We are all out for improving improving our young engineers. And when your president did reach out to me, I felt that this was a very good program to be in. Okay, so I'm really happy to be here as well. Okay, all right. So just before I hand over to your president, or probably I will hand over to your president, I want to know if anybody has any questions. If you have any questions, like I mentioned, there are questions that are the highlights of every single meeting such as this, right? So if you have any questions, please do let me know. You can also address them in the chat box. Okay. All right. So I will be handing over to the executives, the ACES KU executives, to bring the meeting to an official close as we expect the questions. All right.
Hello. Sorry, I had left the meeting by accident.
Oh,
Thanks
it's
a lot. That was an amazing. It was an amazing presentation. It was very brief and direct to the point. I really loved it, to be honest. I know that there are some who might not have understood everything that you said, but then with time, as they go on learning the units, but we still, I still like to give an opportunity for people to ask questions if you have the time, engineer. Otherwise, they can also reach you through your contacts.
all right, gladly, gladly. I'll like I mentioned, answers like I always do see to students that I mentor as well. The quality of your questions is how you know you are growing as an engineer, right? So like questions are always a very beautiful thing. All right, so I have a question here from Bethel. So Bethel says, what answers could you prefer for the questions at the end? All right, so that's a good question, right? So, like I mentioned, there are no right or wrong answers, right? Like I mentioned, the first thing we need to do, for instance, before considering an answer, is to ask questions. I always do mention this thing, questions, questions. It's very important. For instance, now we need to ask, what is the length of the beam? For instance, if we're considering the slab option and the slab question, right? What is the length of the beam? What is the thickness of the slab, right? What material is being used, for instance, right? Let's say, for instance, what area, right? Are those materials available? What is the function? Is it a floor slab? Is it meant to be used as a commercial slab for commercial purposes? Is it meant to be residential, for instance, right? If we're looking at the column questions in this case, we want to see, okay, what exactly is that column structure? What is it supporting? Is it a water tank? What is the length of each of these columns? Why is it failing? What are the values for the analysis, for instance, right? So these are some of the things we want to look at before considering what an answer could be, right? But it is also safe to also consider an answer based on our experience as well, just like I mentioned, earlier on as well. So I hope that was able to answer your question better. All right. So um okay, so I have a comment from Steven. Okay, so thanks for sharing. What would you consider when designing other structures aside buildings? Okay. All right. So Stephen, I would like for you to emphasize when you mean other structures, do you refer to bridges, for instance, dams, hydraulic structures? Just want to confirm if that's the case.
Feel free to open your mic, Steven.
All right. Okay, great. So I'll take it as that, right? So one thing that we don't actually learn, or rather, we don't actually learn in school that is that design of some other structures, for instance, such as bridges, hydraulic structures, are very similar to buildings as well. The only difference it will be, for instance, in the structural codes that we use to design them, right? So, for instance, bridges are basically just a combinations of slabs, beams, and columns. We shouldn't look at it more than that, right? So, for instance, bridges, the slab, for instance, will be the road at the top, right? So we have cars, for instance, those are what we call mobile roads, right? So they're always not always going to be permanent. And if you ask a bridge engineer, for instance, when they are considering loading for bridge structures, they always make sure that they use a loading that would not be too intense on the structure, right? Right. We don't When we're designing bridges, we don't always assume the cars are always going to be on top of the bridge, right? So we have different assumptions when we come to designs of bridges. But the analysis is basically still the same process. It's just going to be some assumptions may be different, right? So bridges, just like buildings as well, also have foundations. They could be supported by spread footings, not always very common. They could be supported by piles as well, right? The same thing also applies for hydraulic structures. In the case of hydraulic structures, you have quite a lot of shear elements, so walls, for instance, retaining walls. You have, for instance, higher reinforced sections to make sure that if, for instance, you are designing a dam, concrete may be a very good material because it doesn't corrode like steel, for instance. And what that means, for instance, is that you have larger layers of concrete, right? But it's basically still the same principles, just different assumptions when it comes to design. All right. I hope that was able to answer your question, Stephen. All right, great. Thank you. All right. So I want to know if there are any other questions before we hand over to the president.
Yeah,
Okay. All right. All right, President.
yeah,
Yes.
I do have a question myself.
All right.
Well, my question is more of a reminder. I was to ask you to maybe brief those who are still here about the opportunity that you had for members pertaining the mentorship program that you're currently running.
Okay, great. All right. So at DANSTRUCT 18, like I mentioned, right, we have a big game in providing, opportunities and also upskilling young engineers, right? We are currently running an internship extension program, which is basically a continuation of one of our just concluded internship programs. And what that program focuses on solely is for you to understand foundational elements or rather foundational topics in building design and produce your drawings, right? So this is a very good opportunity, especially for people that want to, learn how to design buildings and not just learning how to design, but also producing your drawings as well. Now, this particular internship extension program, right, has been designed in a way that you get to collaborate with other young professionals as well from different parts of the continent, Africa as well, share ideas and also come up with solutions to challenges. So you would have referencing drawings, for instance, such as architectural drawings, structural drawings, and as well as also you have guided mentorship as well on how to actually go about your designs. Right. So we are currently running that program, and we are going to. I've been in talks with your president of the association. We are in talks in also having a more inclusive program as well for the ACES community of Kenyatta. So if we can also organize a program where we also have your ACES members, right, also work on project and also produce your own structural drawings as well, in collaboration with DANSTRUCT 18. Also, I should also mention as well, this program is completely free, and we are doing it just to make sure that our young professionals have something, to use for themselves, rather to tend for themselves once they come out of school, as graduates and young professionals, looking to jump into the industry with fresh ideas, right? So yes, it's a program that everybody is free to register for. If you are interested, just feel free to send me a message through some of the platforms you can see on the screen, or reach out to your president as well. He will also direct you on the appropriate steps to follow. All right. Yes. So, yes.
Yeah, thanks a lot. Thanks a lot for that. And yeah, as we had previously agreed, guys. So as you have heard, this is going to be a very beneficial program, and the engineer here is going to admit people based on merit, and we will definitely agree that those who have attended this event will be given priority, and those who have stayed till right now. And something that we have been taking attendance. We have been very keen on your attendance. So those who have stayed till now, this is amazing. It shows your dedication. So you guys are definitely going to be prioritized uh, for the mentorship program. So very soon we're going to open a registration in collaboration with the engineer here. Then we are going to submit the names of and details of the SS members who are interested, engineer. And then after that, we're going to go on. Me included, I'm very much interested to join this program. To be honest, I'm thrilled about construction and structural engineering. So I'm going to be one of those who are going to apply for this. So to the SS members, registration is going to be open soon, and you guys are definitely going to be prioritized. Yeah, and I have a question. What of us from Tuksesa? Yeah, I'm going to have some discussions with the engineer about students from other universities. We are also going to consider you guys. Thank you. That's all from me.
All right. Thank you very much. Yeah, we
Yeah,
do.
by the way, uh, engineer, we don't just have students from KU here. We also have some from Tuk. Some I'm not sure if you joined, but I shared the link with their leaders, so that's why they're here.
All right. So welcome everybody from neighboring universities, right? Okay. All right. So welcome
Yes,
everybody.
yes.
Yes. Welcome everybody. We recognize you. It's great to have you in this program as well. Welcome. All right. Okay. So for those of you that joined as well, feel free, reach out to me as well. My contact is on the screen, and as the president mentioned as well, once the registration is out, he would be the one to direct you on how to go about it. All right. So I hand over to the president now to officially call the meeting to a close.
Yeah, thanks a lot. Nestle, if you can still hear me, you can stop the recording. Thanks a lot, engineer. We really appreciate your time and effort. It was an amazing session, and we're looking forward to having more of these with you and possibly other engineers from Nigeria.
Yeah.
Um, yeah, this is the first. This is the first of our long journey of making SSKU an international association.